second class on Laguerre differential equation. In the earlier class, we have introduced associated Laguerre differential equation to be one which is given by the differential equation y double prime plus beta plus 1 minus x y prime plus alpha minus beta y is equal to 0, where alpha beta are real number, and this differential equation arises in the quantum mechanical treatment of hydrogen atom from its radial part. With beta is equal to 0, it simplifies to Laguerre differential equation y double prime plus y minus x y prime plus alpha y is equal to 0. X is equal to 0 being an removable singular point, we use the Frobenius-Fuchs method. Y of x is equal to summation over k is equal to 0 to infinity ck x to the power m plus k, with c0 not equal to 0 as the trial solution. And the initial equation gives that m is repeated roots of m are 0. So there is only one solution can be obtained from Frobenius-Fuchs method, and it is found that the infinite series solution of Laguerre differential equation diverges asymptotically as e to the power x to the power m, where m is any finite quantity. So to get rid of this divergence, we truncate the solution by letting n to be a non-negative integer n. So alpha can have values 0, 1, 2, etc., and in which case the solution the solution becomes a polynomial of order n and is called Laguerre polynomial, and and which has the series expansion like this: k is equal to 0 to n minus 1 to the power k n factorial square n minus k factorial x to the power k. It is a polynomial of order n, and since even as well as odd powers of x are involved, the ln doesn't have any parity, definite parity, and the question of parity does not arise from the physical requirement, because Laguerre polynomial describes the radial part in spherical polar coordinate. Where now we also obtain the Rodrigues formula as L that e to the power x factorial n dn x to the power n e to the power minus x gives you ln x, and we use this formula for the evaluation of a Laguerre polynomial of few low orders. Now we go to switch over to generating function for Laguerre differential equation. As we have seen in the other two cases, that is in the case of Legendre and Hermite differential equation, that a generating function involves the argument x and a parameter t, and we expand a known series. Here the known function is this: e to the power minus xt by 1 minus t as an convergent infinite series in t. For convergence, t must be less than 1, and this can be shown to be equal to t to the power n ln of x. To prove this, we start with the gxt expression. This is 1 minus t e to the power minus xt 1 minus t. If we expand e to the power function in Maclaurin series, we get 1 minus t summation over r is equal to 0 to infinity minus 1 to the power r x to the power r t to the power r factorial 1 minus t to the power r, which can be written as minus 1 to the power r x to the power r t to the power r factorial 1 minus t to the power r plus 1. Now this this part, 1 minus t to the power minus r plus 1 is 1 plus r plus 1 into t, r plus 1 into r plus 2, t square by factorial 2 and so on so forth, which can be written as summation over s from 0 to infinity r plus 1, r plus 2, r plus s by s factorial t to the power s. If we multiply here the factor of 1, 2, 3 up to r, and these factors are adjusted in the denominator, so this becomes summation over s is equal to 0 to infinity. The numerator is r plus s factorial, and in the denominator we have r factorial, s factorial, t to the power s. So with this, this equation becomes double sum. There is sum of r and s both ranging from 0 to infinity minus 1 to the power r x to the power r t to the power r factorial. It was there. From this we get r plus s factorial t to the power s r factorial s factorial. Now we introduce a new quantity n is equal to r plus s. So there are two sums. One is sum over r, another sum is over n. So this is minus 1 to the power n. This is t to the power r plus s. So t to the power n. This is n factorial. This is r factorial square, and s is n minus r factorial x to the power r, where n is r plus s. We can write it as summation over n is equal to 0 to infinity t to the power n, then sum over r from 0 to infinity. We have minus 1 to the power, sorry, this is my minus 1 to the power r. Minus 1 to the power r n factorial, r factorial square, n minus r factorial. Now you see that when n is equal to r, this term is 0. If r is greater than n, this is negative, and negative factorial is not defined. So there is a restriction on the allowed values of r. R actually ranges from 0 to n. And as r ranges from 0 to n, this part can readily be identified with the Laguerre polynomial of order n, and this expression becomes t to the power n ln of x. N is equal to 0 to infinity, which is the right hand side. Now we shall use this one to get Laguerre polynomial of first few orders. To get this, we use this expansion. This is 1 minus t, this part, and this part is 1 minus xt 1 minus t plus x square t square by factorial 2 1 minus t whole square minus x cube t cube by factorial 3, 1 minus t cube plus t higher order terms. We can write it as 1 minus t to the power minus 1, this is the first term, minus xt, 1 minus t to the power minus 2, plus x square t square by 2, 1 minus t to the power minus 3, minus x cube t cube by 6, 1 minus t to the power minus 4, and other terms. Now, 1 minus t to the power minus r. This expansion, this infinite series expansion with t less than 1 is convergent. It is rt plus r into r plus 1 by 2t square. This is factorial 2 plus r into r plus 1 into r plus 2 by 6 times t cube and so on. So for the first term, r is 1. So this is 1 plus t square plus t cube plus higher order terms. Then for the next term, this is minus xt, 1 plus 2t. This is from this, and this term r is equal to 2 into 3. So this is 3t square plus higher order terms. We have this in this binomial expansion. We have retained up to those terms which gives correct contribution to t to the power cube term t2. So this is the contribution of t to the power cube, and the neglected term contributes to t to the power 4 and higher order. Here similar thing is written, and for for this term we have x square t square by 2. Then here it is 3, so 1 plus 3t plus higher order term, and this is plus, and this is x cube t cube by 6, 1 plus higher order term. So we collect the coefficients of different power of t. So t to the power 0 into 1, the only contribution to t to the power 0 comes from the first term. Coming to the t to the power 1 term, t to the power 1 term, here is a contribution 1, and there is a contribution minus x. Coming to t to the power square term, here the t to the power square term contribution is 1, and this is minus 2x, and here is a contribution x square by 2. Coming to t to the power cube term, this contributes 1 minus 3x. Then this term 3x square, 3 by 2x square, and then minus 1 by 6x cube plus higher order terms. So we can get the result. So we can identify this one with L0, since this is equal to t to the power 0 L0 plus t to the power 1 L1 plus t square L2 t cube L cube and so on so on. So this is L0, this is L1, this part is L2, this part is L3. If we could retain one more term in the expansion, then we could easily get L4. The homework left is find L4. Find L4 from this expression. And now this is the beauty of generating function. We can get higher order polynomials or higher order polynomials very easily. Now we come to the recurrence relation. The recurrence relation is obtained by differentiating the generating function once partially with respect to parameter t and once parallel with respect to argument x. So first thing we differentiate this one with respect to recurrence relations. We first differentiate it with respect to t. So del g del t. If we take this part, we get summation over n t to the power n minus 1 ln of x. Ln of x. And on the right hand side, we will get the derivative of this term with respect to t. So we write it as 1 minus t e to the power minus x u, so that u is equal to t by 1 minus t. So if we differentiate this, we will have del t of e to the power minus x u on minus t. And this is u, so this gives you del u del t is equal to 1 by 1 minus t minus and so if we differentiate this one partially with respect to t to the first e to the power minus x u 1 minus t square, okay, whole square. Then we have 1 minus t is this term, and when we differentiate it with respect to t, this is minus x e to the power minus x u times 1 minus t cube. This is the part del u del t. So if we take e to the power minus x u by 1 minus t, which is the generating function, the remaining term is 1 upon 1 minus t, and sorry, this is square, so altogether it is, this is square, and x by 1 minus t whole square, so that this becomes, for this part we can write, let me first write this part. This is 1 minus t whole square, and then 1 minus t minus x, this part, and for this part we write summation over n t to the power n ln of x. If we multiply this with this, we get 1 minus 2t plus t square summation over n t to the power n minus 1 ln of x. I am not writing the argument, and on the right hand side 1 minus t minus x summation over m t to the power m ln of x. This is an identity in t. So if we, this is an identity in t. So if we collect the coefficient of t to the power k on either side, so coefficient of t to the power k on either side gives you, I hope the part of the screen is readable, this part k, this part contributes to t to the power k when n minus 1 is equal to k, that is n is equal to k plus 1. So this is k, this is k plus 1 L of k plus 1. Second term contributes when n is equal to k. So this is twice k Lk, and this term contributes when n plus 1, when this is n plus 1 is equal to k, that is n is equal to k minus 1. So this is plus k minus 1 L of k minus 1. And coming to the right hand side, the first term contributes when n is equal to k. So the second term contributes when m plus 1 is equal to k, that is m is equal to k minus 1. And the second term contributes again when m is equal to k, so minus Lk. If we take the whole, simplify this one, we get k plus 1 L of k plus 1. This is kept in the left hand side, and every other thing is taken on the right hand side. So this is 2k plus 1 minus x. 2k plus 1 minus x multiplied by L of k, and this minus cancels, and this is minus k L of k minus 1. So the first generating function is there, can be written as k plus 1 L of k plus 1 of x is equal to 2k plus 1 minus x Lk of x minus k Lk minus 1 of x. And knowledge of lowest two orders of Laguerre polynomial enables us to find higher order Laguerre polynomial by using this recurrence relation. To start with, we write L0 is 1 and L1 is equal to 1 minus x. If we put k is equal to 1, so we get 2L2 is equal to k is equal to 1, so 3 minus x L1 minus L0. I have used k is equal to 1, so this is 1 plus 1, 2. This is 2 plus 1, 3 minus x, and k is equal to 1. So we know that it is 3 minus x into 1 minus x minus 1. So this is 3. This is minus 3x minus 4x, and this is x square minus 1. So this is 2 minus 4x plus x square, which gives you L2 is equal to 1 minus 2x plus x square by 2. And knowledge of L1, L2 enables us to find out L3. So with k is equal to 2, we get 3L3 is equal to 5 minus x L2 2L1. From this relation, explicit use of this, we can find the value of L3. Now I am going to the other recurrence relation that can be obtained by differentiating this relation partially with respect to argument. So del g del x gives you from this part summation over n Tn ln prime of x. Actually ln prime of x stands for d ln of x dx. And if we differentiate the right hand side, we get 1 minus t, and then we have this is xt divided by 1 minus t. So sorry, this part should be written over here, minus t, 1 minus t e to the power minus xt by 1 minus t. Now, if we relate this part and this part together forms a generating function. So we can write it as minus t by 1 minus t g of xt. So this is minus t upon 1 minus t summation over m t to the power m ln of x. Or we get this is multiplied to the 1 minus t summation over t to the power n ln prime minus t to the power m ln of x. Again, this is an identity, and t to the coefficient of t to the power k on either side. The first term is lk prime, and this is l prime k minus 1, and is equal to minus lk minus 1, or we get lk prime of x is equal to l prime k minus 1 of x minus lk minus 1 of x. This gives you the derivative of a particular order of Laguerre polynomial in terms of the Laguerre polynomial of a lower order and its derivative. Say for example k is equal to 1, so this relation gives L1 prime is equal to L0 prime minus L0. We know that L0 is 1, so this is minus 1. So on integrating, we get L1 of x is equal to minus x plus some constant C1. Recall that during the series expansion, we assumed C0 in such a way that ln of 0 is equal to 1. So if we push that condition, C1 comes out to be 1, and we get it as 1 minus x. Coming to L2. L2 prime is equal to L1 prime minus L1. L1 prime is minus 1, and L1 itself is 1 minus x. So we get it as minus 2 plus x. On integrating, we get L2 is equal to minus 2x plus x square by 2 plus c2. Again, if we set that L2 at 0 is 1, this gives c2 is equal to 1, and this becomes 1 minus 2x plus x square by 2. So we can get the Laguerre polynomial of higher order as well as the polynomial itself.